All right, so now we're getting to a new situation. The first, when we were talking about elements in a group or in a row, the elements themselves were different, right? It was a OH bond versus an NH bond, or a BRH bond versus an FH bond. But now the acids that we're comparing are both OHs. So we have to go a little bit deeper than what atom it's connected to explain the relative acidity of those groups. And one of the factors that controls this is something called an inductive effect. And what is induction as far as chemistry? Induction is the pull of electron density by electronegativity differences between atoms. So essentially, if there is a difference of electronegativity, those atoms are pulling the electron density away. And what we know about conjugate bases and their relation to acidities, if we have more delocalization in the conjugate base, we had a that greater delocalization came from a stronger acid. I think is all I was trying to say there. So the more delocalization comes from stronger acid. So if we have two different species, one of them's more delocalized than the other, the more delocalized one came from the stronger acid. It's a more stable conjugate base because of that extra delocalization. So here, let's again think, okay, well, fluorine on this molecule here is electron withdrawing, and it's going to do that inductive process that we just talked about. So how does that impact the acid? How does that impact the conjugate base? So go ahead and draw your arrows, draw the conjugate acid, conjugate base for these two examples with the arrow pushing, and then come back. Okay, you did that, good job. You thought about it. So again, the base is going to grab the protons to form the conjugate base and the conjugate acid, and here the same situation, but just a slightly different molecule, a CF3 there. I'll just write CF3 in this box. So how does that CF3 impact the acidity of that OH bond? Okay, so fluorine's pulling electron density away. How does that impact the acid? So something that you have in your packet is actually the electrostatic potential map of that molecule and that molecule. So I want to draw your attention to your packet right now. And what you see is that the OH bond in ethanol, this first molecule here, is really just kind of slightly blue. And what blue indicates, the more purple you are, the more positive charge there is there. And blue is on its way to purple. And what you see is that where that H is in that electrostatic potential map, it's blue, but it's kind of a light blue. What we see in this one, on the other hand, is that where that H is in that electrostatic potential map, which I unfortunately have a gray copy here, but it's right there on your notes, is almost purple. And that purple color shows that it's got a very large partial positive on it. So why is that? Why is this one only partially positive and this one is very, very much partially positive? And it's because these fluorines are pulling electron density away from that. So again, let's redraw that molecule right here. I'm going to put the stereochemistry in a little bit. So what are these fluorines doing? They're more electronegative. So they're pulling electron density away from that carbon, and each of them has a partial negative. And all three of those partial negatives have to be balanced by the partial positive that's right here. So we have an enormous partial positive on that carbon. And because of that huge partial positive, it's actually going to be pulling electron density away from its neighboring carbon, which generates a partial positive there, which is going to even further down the line put a partial positive right next to the partial negative, because this oxygen is electronegative, right? It wants to pull electron density toward it, but it is not going to be able to pull much because of those fluorines also inductively withdrawing to make a much greater partial positive on that hydrogen right there. And what I'm going to draw here on the oxygen is a partial positive that's because of these fluorines drawn away, but this oxygen is actually able to pull electron density from both of those. So it's actually it is negative itself, but I'm just going to draw those charges next to each other because they are, the partial negative it's pulling harder because of that inductive effect of those fluorines. So here, comparing this hydrogen to the hydrogen from ethanol, this is just going to pull there. It's going to have a partial positive next to it, but this one's much greater because of the inductive effect of those fluorines. So the base would rather go to the much larger partial positive. So those fluorines actually destabilize the acid, making it a stronger acid. What's their impact on the conjugate base though? Well, if we think about the conjugate base, we have O minus there, so there's a negative charge on the oxygen, not the most ideal thing. And then we have those 3 fluorine atoms. So here, the induction destabilized. So it destabilized the acid here. It's destabilized. On the conjugate base, it's a negative charge on that oxygen, so the inductive effect of these 3 fluorines is actually going to stabilize that conjugate base. So here, the induction stabilizes. So that's a really important thing about induction. Induction stabilizes negative charges, it destabilizes positive charges because it's pulling negative charge away. Having 2 opposite charges right next to each other is a stabilizing force. The extra unstable negative charge here can kind of delocalize onto that positive charge there. So that's why it stabilizes here, but the positive here is growing larger because these fluorines are pulling negative charge away from it. So which one was more acidic? This one was more acidic because of the reasons that we just talked about. So yeah, so that's how induction works. Let me know if there are any questions on that. One more thing, forgot to mention in that last video, I was going to put up the pKa values for ethanol versus trifluoroethanol on your note packet. And it turns out that the pKa of ethanol is one that you know, 16, and trifluoroethanol, the one that was more acidic, is 11.3. So what we see is that inductive effect dropped the acidity, it increased the acidity to a pretty enormous extent if you think about it. Remember that each pKa unit, so if something had a pKa of 12 versus 13, this is a log scale. So the one that had a pKa of 12 is actually 10 times more acidic than the one that had a pKa of 13. So that difference of 16 versus 11.3 is enormous. It's that difference of numbers 10 to the that. So keep that in mind as you're thinking about these acidity trends.